Hello everyone. Let's start our new chapter. The new chapter is organic chemistry, and in this chapter, we will talk. We will introduce organic chemistry and try to understand what is organic chemistry. Organic chemistry, at its core, is simply the study of carbon-containing compounds and their reactions. Historically, the field of organic chemistry got its name organic because scientists initially believed these complex molecules could only be created by living organisms, hence the name organic. However, sci- the definition of organic chemistry later changed when they discovered how to synthesize this compound in the lab, and that led to the modern definition of organic chemistry. Uh, why do we care about organic chemistry? What is the importance of organic chemistry? Simply put, organic chemistry is the chemistry of life. The foundational molecules that make up every living beings, every living things on Earth are organic. We are talking about, for example, DNA, which carries your genetic code, all the proteins which do the work in your cells, and your fuel sources like fats and hydrocarbons. Uh, but the organic chemistry also extends far beyond just this biology. Uh, if you look around you, most materials we interact in our day-to-day life are organic compounds. Uh, for example, a majority of medicines are also medicines. Plastics is made out of organic compounds. The fuel we use in our vehicles are also organic compounds, and this all the clothings we wear are also based on organic compound. To understand organic compound, let's first create a contrast between organic chemistry and inorganic chemistry. If we look at the comparison table here, the key difference is the element involved in this compound. Organic compounds are based on carbon and hydrogen, whereas inorganic compounds are mostly uh, metals or ionic compounds. And this elemental difference dictates everything else. For example, the bond type, melting point, solubility, etc. Organic compounds use primarily covalent bonds, meaning they share electrons instead of transferring the electrons like in ionic bond. Because of their covalent bond, which is a weaker intermolecular forces, organic compounds tend to have usually low melting and boiling point. Uh, and if we look at inorganic compounds like salt, and their melting points are pretty high compared to organic material. And the solubility is also, organic compounds are generally soluble in organic solvents, whereas inorganic compounds are soluble in water. And some of the few example, the most common example, petroleum and glucose are organic compound, whereas the salt, NaCl, and calcium carbonate like lime, chalk we use in our classroom are example of inorganic compounds. And since we said the organic chemistry is basically simply the study of carbon containing compounds. So why carbon? Let's talk about why is carbon so important in organic chemistry. And the entire field of organic chemistry rests on one element, and that is carbon, as we said. And the magic of whole this organic chemistry is on this atomic number of a carbon. As we know, the atomic number of carbon is 6. The and if the atomic number is 6, and if we look back to our electronic configuration, we we find that the valence electrons of carbon is 4, and this is also called tetravalency, meaning tetra is for 4 and valency is the number of electrons in the outermost shell. So carbon has a tetravalency, and this property is what uh, gives carbon different ability. And the first is catenation. Catenation is the ability to bond strongly to other carbon atoms. That means carbon can bond with other carbon atoms, and this property is called catenation. And carbon can form long stable chains, rings, and different complex structure. And this catenation, meaning bond between different multiple carbon atoms, uh, is why we have millions of non-organic materials. And then the second property, this tetravalency provides for carbon, is the versatility. Carbon doesn't just bond to itself, it bonds with a huge variety of other elements. Example: hydrogen, oxygen, nitrogen, sulfur, and different halogens. This molecular flexibility makes the combination of these organic compounds virtually limitless. As we mentioned, carbon achieves its stability by forming covalent bonds, sharing, which basically means sharing electrons with other atoms. Carbon must also have a total of 4 shared electron pairs at its outermost shell. That means carbon can achieve this stable outermost shell by 3 different ways. First, carbon can form a single bond, then it can also form double bond and triple bond. First, the single bond of carbon can be with carbon and carbon, or carbon and hydrogen, and in the single bond carbon shares just one pair of electrons. And an example of a single bond is methane. We can see here there is 1 carbon and 4 hydrogen, and as we know, hydrogen has a valency of 1, carbon has valency of 4. So in order for a carbon to complete the outermost shell with 8 electrons, it must receive 4 more. So we can say this carbon will get 1 electron. It will share 1 electron with one of the hydrogen, 1 electron with other hydrogen, hydrogen, so on. So it will form a single bond with hydrogen, and the simplest example is CS4, and we call this material methane. Similarly, double bond, as we can see, is generally represented by this double line, and in double bond carbon shares 2 pair of electrons with as we can see here, double bond in a double bond covalent bond, carbon shares two pair of electrons, and the simplest example of a double bond is hydrocarbon is ethane. And as you if you look at the molecular formula of ethane, we can see there are 2 carbon and 4 hydrogen atom. That means if you look at the valency of carbon, we know it's 4, and since there are 2 carbon, there should be 8 there should be 8 extra pair of electrons to share with carbon to complete its outermost shell. But if you look at here, we only have 4 hydrogen. That means carbon have to form this double bond with the other carbon in order to complete in order to complete its outermost shell, in order to fill its outermost shell. So if you look at here, so each carbon is already sharing 2 electrons. Now we know it should be 4, so 1 2 3 and 4. This will be 1 2 3 and 4. Now we know this carbon, the outermost shell of this carbon is complete. Similarly, we'll have 4 hydrogen and hydrogen. So we can see from here, with the double bond, this molecule achieves the stable electronic configuration of carbon. In the similar way, if we look at triple bond here, and the simplest example is ethane. We have 2 carbon, only 2 hydrogen. So if this is the structure, then what should we have? Carbon should have one more pair of electrons sharing between them. So we have 3 triple bond, and the fourth electron carbon needs will be provided will be shared with hydrogen atoms. So triple bond, and the simplest example of triple bond is ethane. And we can see the bond strength in a covalent bond of carbon in these 3 different types. The strength of this bond is highest in the triple bond, and it's in between triple and single bond for double bond, and the lowest strength is for single bond. So in other words, we can say that a triple bond is the strongest bond, followed by double bond, and single bond is the weakest. Now let's put this the octet rule to the test. Remember, carbon needs 4 bonds, and if we look at this first diagram here, there is carbon and nitrogen. So we should also know that the valence electrons of nitrogen, atomic number of nitrogen is 7, so 2. So if we look like this, first we can have 2, then remaining is 5. So valence electron is 3 for nitrogen. So carbon valence electron 4, nitrogen valence electron 3. Let's also look at the second example. There's chlorine, so valence electron is 1. And now if we look at the first one, as we know, each atom should complete their outermost shell with 8 electrons. If we look at this first one, carbon, there is one pair of electrons shared with this carbon here. So that means we still need 3 more hydrogen. Now if we look at here, 1 2 3 and 4 electron pairs. So this carbon, the first carbon here, is now stable because it's the outermost or the octet rule is complete, because one bond here, second bond, third bond and fourth bond. Similarly, the second carbon. Now if we look at this second carbon, we can see, and this is already sharing one bond here, second bond here, so it will require 2 more hydrogen. Similarly here, hydrogen, hydrogen, sharing 1, sharing 1, 1, 1. And if you look at nitrogen, nitrogen has a 3 valence electron. If you look at here, it's sharing 1 bond here, second bond here. That means it requires 1 more hydrogen, like this. And the same way we can draw this bond for the second figure, and the solution we can see here. For the first plot, for the first compound, we can see here nitrogen will have 1 more extra bond, because this is nitrogen has 3 valence electron, 1 2 and 3, and all the carbon atom have 4. So 1 2, oh sorry, this will also have 2, because at the end this will also have a complete octet. Similarly, if you look at the second diagram, the first one is oxygen. Oxygen is valence electron, atomic number of oxygen is 8. So the valence electron in oxygen is 2. Now oxygen requires 2 bond. So we will have 1 oxygen here, and since it already is bonding, there is a single bond between oxygen and carbon, the octet rule is completed. So there will be 1 hydrogen. Similarly for carbon, 1 bond here, another bond here, so this will require 2 more hydrogen bonds, and so on. So if you look at the center, oxygen requires 2 bonds, which is 1 bond, 2 bonds, so there's no other hydrogen. Similarly chlorine is the valency is 1, so the single bond here is sufficient to complete the octet rule. Now let's look at the simplest organic compound. We call them hydrocarbons. Hydrocarbons, as the name suggests, hydro and carbon implies these compounds contain only hydrogen and hydrogen and carbon. And we classify this simplest organic compound or hydrocarbons into 3 main types based on the bonds they contain. The first is alkanes, and as we can see from here, alkanes contain only single bonds, single carbon to carbon bond, and these alkanes are saturated, meaning there is the highest possible number of hydrogen atoms it can contains. That means we call this nature of this compound that if the number of hydrogen atoms in this hydrocarbons is the maximum that is possible, then we call them saturated. If it's not maximum possible, then we call them unsaturated. And if we see here in the alkanes group, since the bond between carbon is only single one, that means if we look at here, we can see the maximum possible hydrogen atoms that can combine with the carbon is 4, because the balance is 4. We can see this is saturated with hydrogen. It cannot take any more hydrogen. So we can say alkanes are made up of single bonds, and these are saturated compounds. And the suffix we use for this kind of material is ane, and the organic compound in this group follow this general formula of CnH2n+2, and this n will start from 1. So if we substitute C equals to 1, what will it be? C1H, this will be 2 plus 2, 4. So this is basically what a methane is, right? And then we have alkenes, and the suffix we use for alkene is ene, and the definition of alkene is that this compound will have one or more double bonds, double carbon bonds. And as we see, since there is a double bond between carbon and carbon, it is expected that it will take fewer hydrogen than it is possible to alkanes, meaning this group of compound are unsaturated. And the general formula for alkene group is CnH2n, and since there has to be two carbon atom to form a double bond, we can see here the first n value starts from 2, so this will be C2H4, and this is ethene, and ethene is the simplest alkene compound. And then we have alkynes with the suffix yne, and these contain one or more triple carbon bonds. They are highly unsaturated and follow the general formula CnH2n-2, and the ethine is the simplest example of alkynes group. Sorry, there's a typo here. Simplest compound of alkyne groups. And we also have this aromatic hydrocarbons on top of these 3 bonds. On top of these 3 groups, we also have aromatic hydrocarbons, and these aromatic hydrocarbons are characterized by rings with alternating single and double bonds. And a most common example of aromatic hydrocarbon is benzene, and we can see here there is a double bond, single bond, double bond, single bond, double bond, so basically an alternating double bonds. And we can also represent this in this form. So this is the most common representation of benzene. When we talk about organic chemistry, we have several ways to represent them, each providing a different level of details. The first one is a molecular formula, which is what we have been using in the previous chapter. And this molecular formula is the most basic, and this molecular formula simply tells you the type and the number of atoms in the molecule. but this molecular formula does not show how these atoms are connected. For example, we can see methane is CH4 and C2H4 is ethane, and so on. And then we have structural formula, and this is where we start to show the connection and how these atoms are structured to form the molecule. And the structural formula shows all the atoms and their bonds as line. We already saw an example of this kind of structure in previous slide. For example, if we take an example of propane, the structural formula will be CH3, CH2, CH3. And if we were to write the molecular formula of this compound, that will be C3H8. And if you look at this molecular formula, we cannot say how they are combined, but if you look at the structural formula, we can see at each end there is CH3, and in the middle there's only CH2 forming a single bond here, right? And then we have this condensed structural formula, and this formula is used in a textbook. This is what is most common to represent this organic molecules in textbooks, because it saves space by grouping the hydrogens with the carbon atoms they are attached to, making it easier to type. And for example, if we look at the same example from here of the propane, we can simply write it, instead of using this dashed line, we can simply write CH3, CH2, CH3, and it will imply the same structure. And then there is skeletal or line formula, which is the most common way to represent complex organic molecules, and it uses this line structure of a combination of zigzagged straight lines like this. Here we can see here there is one line, second line, other line, and other line to represent the organic compound, and this is called skeletal or line structure. And as we say, this skeletal structure or line structure is the ultimate shorthand in organic chemistry, and it makes representing these complex molecules easy to draw quickly. And this process, this creating skeletal structure, operates under few simple rules, and the rules are as followed. The carbon atoms are implied. We assume a carbon atom is at every vertex or corner, and at the end of every line. For example, if we look at here, what does it say? It says carbon atoms are implied at every vertex or at the end. That means there should be a carbon here, 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 and here. And if we look at the molecular formula, there should be 5 carbon, right? 1, 2, 3, 4, and 5 carbon. Similarly, second, hydrogen on carbons are implied. As we said, hydrogen will combine with carbon for this to complete the octet rule. And this since most of the organic compounds are made of hydrogen and carbon, hydrogen are also implied whenever there is a carbon and it requires some more bond to complete the octet. It is implied that it is bonding with hydrogen. For example, if we go back to this example here again, if there is a carbon and there is one bond here, that means we should have 3 carbon here. If you look at this carbon, it has one bond here, second bond here, that means it will require 2 more hydrogen. Same here, one hydrogen, one hydrogen, one hydrogen, one hydrogen. And if you look at here, this is only one bond, so it will require 3 hydrogen. Now if we count the total number of hydrogen here, 3 3 6 7 8 9 10 11 12, right? So if you look at the molecular formula, this is C5H12, and if we count the number of carbon and hydrogen, we will get the same. So basically what we can say, this is the molecular formula, and the second is condensed structural formula. So this is condensed structural formula, and this is line or skeletal formula. And the third rule on drawing this skeletal formula is that other atoms must be drawn. Any atom that is not carbon or hydrogen, for example oxygen, nitrogen, chlorine, etc., are called heteroatoms. Sometimes these are called heteroatoms, and these atoms should explicitly shown in the in this line diagram. For example, if we look at ethanol, the molecular formula is C2H5OH, and the condensed structural formula is CS3, CS2, and OH. And if we want to draw the line structure for this, we can see there should be 2 carbon, that means 1 carbon, other carbon, and there should be 5 hydrogen, right? And if you look at this diagram, we know there is 1 bond here, that means this carbon should have 3 hydrogen bond, and the second carbon, single 1 bond here, 1 bond here, should have 2 hydrogen, and the third is OH. And if we count all the atoms, we can see 2 carbon, 5 hydrogen, and 1 OH. And the molecular name of this structure is ethanol. This nol comes from this OH functional group. So the summary is that whenever we have some heteroatoms like oxygen, nitrogen, chlorine, etc., we should explicitly show them in the line structures. However, we don't have to explicitly show carbon and hydrogen atoms. Before we can we move to complex structures and we start naming this complex structure, we need to know the basic prefixes, or these are also called stem here, based on the length of the continuous carbon chain. We talk about the basic formula before. Here we can see CnH2n plus 2 is for this alkane group, and as we can see, if n equals to 1, this is CS4, n equals to 2, C2H6, n equals to 3, C3H8, n equals to 4, C4H10, and so on. And based on this number of n, here we have different prefix for naming this, and when n equals to 1, we call it meth. And if we are looking at the alkane group, as we talked about in previous slide, when there is alkane, we said the prefix we use is the suffix we use is ane, so this will be methane for alkene group, and this is eth for n equals to 2, so this will be ethane. When n equals to 3, then that will be prop, and then suffix is n, so propane. Similarly, but will be butane, pent will be a pentane, hex will be hexane, and so on. And if we go back to previous slide where we talked about alkane, alkene, and alkyne, we said each group has different suffix here, and if we were to name a compound from this group, or the organic compound that has a double bond, we would say this will be what will this be when n equals to 2? This will be ETS is the same because that's the naming prefix, so ethane, and as we know from previous slide, the suffix is ene, so then this will be ethene, and this will be propane, butane, pentane, hexane, and so on. Similarly, if you look at the third group with the triple bond, we said that it will have a suffix of yne. So if we were to name those compound based on this, what will we say? This will be it, with the stem will be it, and then the suffix will be thine. So this will be ethine, propane, butane, pentane, and so on for alkyne group. So in order to name this structure based on this number, this n value, we will name this is compound using stem and suffix based on the bond it's forming. And organic nomenclature follows a systematic set of rules known as IUPAC or IUPAC, and we have to follow the standard procedure of naming this structure. And the basic rule for naming organic structure are mentioned here step by step. First, identify the parent chain, and basically find the longest continuous carbon chain, and this will gives you the primary stem name. Like we said before, it will give us meth, eth, hex, or whatever the number of carbon is, and then we will look at the number of chains number, and this number of chain is basically the number of carbon atoms starting from the end that gives the lowest possible number to the first substituent or side chain, or we can say for substitute or side chain. And then after that we will name this side chain or substitute, and we will again use the same stem with YL suffix instead of ANE, ENE, sorry, instead of ANE, ENE, or YNE, we will use YL. For example, here that will be methyl, ethyl, etc. And then we will use a multiplier here. We can see if the same substitute appears multiple times, we'll use prefixes like di for 2, tri for 3, tetra for 4, etc. To name this side chain or substitute, and then at the end we will assemble the name. We will list the substituent in alphabetical order, ignoring the multiplier like di or tri. For example, if we have dimethyl triethyl, then we will first ignore this di or tri, and we will want to look at methyl and ethyl. So we will list them in alphabetical order, ignoring prefixes like di, tri, etc. And then we will place the number locator before each group and finish with parent chain's name. Let's look at a few examples to understand this rule. First, we have 3-methyl hexane. So let's forget what the name is, and let's just look at this structure here. If we look at this structure, first we can figure out the longest chain. So if you look at here, there is a chain here and a longer chain here. So this is the long chain or the parent chain, because if you count number of carbon, we have 1 2 3 4 5 and 6, and this one, if you count here, this is only 2 carbons. So the longer chain or the parent chain is 1 2 3 4 5 and 6. And if you look at here, this is single bond, single bond, single bond, single bond, single bond. That means, and this is alkane group, right? And if we look, if we count the carbon, there are 6 carbon. That means this will be hex, meaning 6. And then we also know single bond, so it will be hexane, right? So the parent chain is hexane, because there are 6 carbon, and all this carbon bond are single bond. And as we said from the rule just in the previous slide, we will look at this chain and start numbering it. And if we start numbering from left to right, what will it be? This is 1 2 3 4 5 and 6. So we could say this is 4, or we could say this is, if we were to count from here, this is 2, right? And in order to count this way, we will always want to count such that the number is lowest. So we will not count 4, rather we will say this is 2. And what is this side chain? This is CH3. This is only 1 carbon and 3 hydrogen. That means this is methyl group, the first group, right? And if we combine all this information, we got, sorry, then this is not 2, this is 3 from here, so this will be 3. What will the name of this compound be? This will be 3. And as we say, we will add this extra chain as YL stem plus YL. So if it is methane, then methyl, ethane, it will be ethyl, and so on. So if you look at here, this extra group is based on methane, so this will be 3 methyl. And as we say, the main chain is 1 2 3 4 5 6 with 6 with single bond, so hexane. The name of this compound is 3-methyl hexane. And if we were to represent this structure with a skeletal or line structure, we can see carbon will be here, 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 and a side chain will have a line here. And since this side chain is also hydrocarbon, we don't have to represent by anything, and we can draw it like this. Now if we look at the second example here, we can see there are instead of one chain in here, we have multiple chain, one extra substituent here, so extra chain side chain here, and extra side chain here. Again, we will start with counting number of carbon in the main chain. If we look at main chain, how many carbon do we have? 1 2 3 4 5 and 6. Again, all the bonds are single carbon bond, so now we know this will be hexane. So the main chain is still hexane. And if we look at this side chain, we will start counting, and we will count such that the number will be smallest. So what will be the number? We'll count as 1 2 3 4 5 and 6. So if you look at here at 2, instead of just one side chain, we have one side chain in this direction, other side chain as well. So that means we have 2 and 2. And if you look at this fifth side chain, is the same material, same compound here. This is CS3 CS3 CS3, so we can say these all are same, and after these numbers we will use a dash line. And if we look at if we go back to our slide, we said we will assemble all these names with this prefixes like di, tri, based on how many are there. So if you look at here, there is 3, so this is CS31, CS32, CS33. So what will be our name? This will be tri, and CS3 is again based on methane, so we have to say methyl. And how many what is the name of the parent chain? That is hexane, right? So hexane, the names will be 2,2,5 trimethyl hexane. One more example, if we look at here, now if we count a number of carbon in the main chain here, again this is 1 2 3 4 5 6. So the chain parent chain is still hexane. And if we look at this side chains, this is methyl. And if you look at here, this is still single bond but 2 carbon, that means this will be ethyl, right? And again, we said we have to start numbering, and we have to write the structure such that we will write these names in alphabetical order, right? So as we said, this is ethyl and this is methyl. And now if we combine all this name, so this is 1 2 3 4 5 and 6. What can we say? It will have, as we said, it will be arranged in alphabetical order. So this will be at position 2 we have ethyl, and then at position 5 we have methyl, and as we say, the parent chain is hexane. So the name of this compound will be 2-ethyl 5-methyl hexane, as we can see here. And if we were to represent from with the line structure, this is the parent structure, and if we look at here, there's a side chain, and side chain has 1 carbon here, 1 carbon here, so this is ethyl group, and this side chain one has 1 carbon, so this is methyl group. Now with that, let's introduce functional groups or and carbon derivatives. We can start with carbon derivatives. As the name suggests, carbon derivatives are, So these are derivatives of carbon, and these carbon derivatives are formed when we replace one or more hydrogen atoms on a hydrocarbon with some other element or group of elements, and this is how we get families of compounds like alcohol, halides, amines, etc. So basically, if we look at the image here, so methane will have, methane is basically carbon with 4 hydrogen, and if we were to replace this one of the hydrogen with OH group, now we will get methanol. So this is a derivative of hydrocarbon with OH, and this hydrocarbon derivative, the substance, this hydrocarbon derivative, or we can say the element or group of element that creates these hydrocarbons are called functional groups. So if we look at here, in methane there is hydrogen, and in methanol there is OH. So this OH is a functional group, and this, as we said, the, these elements are the functional this element or the group of element that replaces hydrogen are called functional group. And this functional group are responsible for the chemical and physical properties of organic compounds, and these functional groups are both responsible for functional groups are responsible for characteristics reaction of organic compound, physical properties of organic compound, as well as this organic group is used in naming and classification of organic compound. We can see from example here, so this is the previous example we just saw. Any organic compound with functional group OS, we call them alcohol, and as we saw from a previous example, this OH here, and we can see everything is single bond. So this is alkane group, and there's only one carbon, meaning that is methane. And since there is a functional group OH here, instead of hydrogen there is a bond with OH, and we know from here that the functional group with functional group OH, the naming convention will be alcohol. That means this the name of this structure should be methane plus alcohol, basically methanol. And you can see different examples of a functional group here, and as we say, changing just one functional group completely changes the chemical as well as physical behavior of the entire compound. Finally, let's look at the concept of isomerism. Isomers are molecules that have the same molecular formula but different structures or arrangement of atoms. This difference in structure is key because if the atoms are connected differently, the compound will have different physical and chemical properties. And there are several types of isomers, and the main or the common type of isomers are chain isomer, positional isomer, and functional isomers. And let's start with the example of a chain isomer. Chain isomer have same formula, but the carbon chain is arranged differently. Example, we can see here N-butane and isobutane, where a straight chain where we can see a straight chain of carbon versus branched chain of carbon, straight chain of carbon in N-butane versus a branched chain of carbon for isobutane. However, if you look at the molecular molecular formula, we can see there are 1 2 3 4 carbon, and if we count hydrogen, there are 3 5 7 10, right? So the molecular formula is same for both scenario, but they have a chain. The first one has a chain structure and the second one has a branch structure, and this kind of isomer are called chain isomer. And the second one is positional isomer, and positional isomer are also the same formula, but a functional group is in a different location of the chain. So in first example, we can see the functional group is at the ends of this compound, and if we were to name it, this will be 1 bromo butane. And if we look at here, the functional group is at the second position instead of first position here, and if we were to name this will be 2 bromo butane. And the molecular formula is same for both cases, but they are different in their structure. And as we see, based on the position of this functional group, they can form different isomer, and this kind of isomer are known as positional isomer. And then we have functional isomers. Again, same formula, but they have completely different functional groups. Example, we can see here alcohol and ether. So if we look here, just before we said a functional group OS is called alcohol, right? And if we look at this second one here, this is ether with OH, but if we were to count number of oxygen, carbon and hydrogen, we will get the same molecular formula, but if we look at the structure, the functional group here is OH and here is just oxygen. So based on functional difference in functional group, we can get different isomers, and this kind of isomers are called functional isomers,